So let us define an elliptic curve. The elliptic curve E over some given field K is a smooth curve of genus 1 or degree 3. So this is equivalent. So we have seen in the lectures on algebraic geometry that you can compute this genus G as this d minus 2 times d minus 1 divided by 2, where d is the degree of the curve. So if you put 3 here, you will get genus as 1. So this elliptic curve E also comes with a special point, which you write as calligraphic O. And by convention, this calligraphic O is set to 0, 1, 0. So that is, we are working in space P2. And this is called the point at infinity. So this entire thing 0, 1, 0 is called the point at infinity. Now we have seen in the lectures on Riemann-Roch, that is in the playlist Riemann-Roch, that this genus 1 curve, this translates via Riemann-Roch to a Weierstrass equation of this form. So this we have shown in the lectures on Riemann-Roch. Now since we are working in P2, it's homogenized version of degree 3. So you have to put a z here to make it degree 3. So y square is there, so you make it degree 3 by putting a z here. This is degree 2, so put a z here. This is degree 1, so put a z square here. As you can see, this is already degree 3, so you don't do anything. This degree 2, put a z. So this is just degree 1, so put a z square, so you get degree 3 everywhere. So this is degree 0, so you put z cube. So each of these coefficients, a1, a3, a2, a4, a6, all of these lie in our base field K. So this is the homogenized version. So let us see some examples. So two examples which we are going to see is, number one is this congruent number curve, which is y square is equal to x cube minus n square x, where n is a natural number. Second example is this Bakke model curve. So y square is equal to x cube plus c, where c is a non-zero integer. So if characteristic of our underlying field K is not 2, then we can make a substitution. So the reason we are making a substitution is because, this seems really long to us. We want something simpler. So the details of the substitution you can find in this book, Arithmetic of Elliptic Curves by Silverman. So this is on page 42 and 43. So we make the substitution because we want to make our life easier. So you make the first substitution. Y you write as half y minus a1x minus a3, and you get this simpler equation, which is we call the medium Weierstrass equation. And you have these new coefficients b2, b4 and b6, and these b2, b4 and b6, these are related to the previous coefficients like this. This is a1 square, a4, b4 is 2a, 4a1, a3, b6 is like this. Now if the characteristic of your underlying field K further to not being 2 is also not 3, then you can make a further substitution. So now you introduce this 36 here, and that's precisely why we did not want 3. So x is transformed to x minus 3b2 over 36. You see this 3 is also here, and this y over 108. So again, this is divisible by 3. So therefore we want the underlying field should not have characteristic either 2 or 3. So if you make this substitution, then you get a further shortened equation. So you get a short Weierstrass equation of this form: x cube minus 27 c4x minus 54 c6. Again, this c4 and c6, these are related to b2 and b4 right here. All these coefficients here, b2, b4, b6, will be fed in here. So c6 is again related to b2 and b4 and b6. So again, all these details you can find in the book here, Arithmetic of Elliptic Curves by Silverman. So if the characteristic of our elliptic curve is not 2 or 3, you essentially make your curve easier. So this is the kind of curve we will study. Y square is equal to x cube plus ax plus b. So it looks simple, looks easy. So corresponding to this curve, there is a discriminant. So this is the discriminant of the curve. So there is a 16 here, which is a constant. But if your discriminant of the curve is not 0, then it automatically ensures smoothness. So if you have a curve like this, you compute its discriminant, then it gives you smoothness, then you immediately know this is an elliptic curve. So elliptic curve could come in this simple form: y square is equal to x cube plus ax plus b. If a curve is given to you like this, compute its discriminant. If it is not 0, that ensures it is smooth, and therefore it becomes an elliptic curve. So So this is the most common used form. Now in this book, Fermat's last theorem, this book is volume 1, which is Basic Tools by Sato. He uses a different form. So obviously you can again transform this curve into this form here, or you could just go from here to here. So you could transform this entire curve here to here. So again by substitution. Now if you have a curve like this, so now you have 4x cubed minus some constant ax minus b. Then the discriminant is given as a cubed minus 27b square. So if this discriminant is not 0, then you again have a elliptic curve. So let us see an example again taken from this book, Fermat's last theorem, Basic Tools. So by Sato. So you have this curve y square is equal to 4x cubed minus 4x square minus 40x minus 79. Now you can transform this into a smaller equation, y square minus 4x cubed, and then you have this coefficient here times x, and then you have another coefficient here. So precisely this form, you have an a, you have a b, and this is the change of variable is given to you. X is just transformed to x plus 1 by 3. So just a single transformation of x is done. So you can go from this general form here to something simpler like this. Now you can compute the discriminant of this. The discriminant is a cube minus 27b square. So you have a cube minus 27b square. So this is our b, which is right here. This is our a, which is right here. We are working with this form. Compute this. This is minus 11 to the power of 5, which is not 0. So we get that this was an elliptic curve to start with.